Um, I'm gonna I'm gonna give this a test run. I don't know how well this is gonna work yet, but I'm trying something new, just because typing in Word and drawing all those pictures has been frustrating to say the least. So here we go. I know my handwriting's pretty bad. It's a little better in person. It's gonna be really bad on this tablet thing that I'm using here. But we'll see how it goes, and if I need to go back to using Word to write stuff up, I'll go back to using Word. But this is a continuation here. We are still in 6.1. Remember, we're doing the disk method. Disk method. Oh, this is going to be hard. Okay, cool. Just a second. All right, sorry about that. I got a text message from the boss, so I had to deal with that. So remember with the disk method, we're finding the volumes. And to find the total volume of the disk method, it's the integral from wherever your limits are going to be, a to b, of pi, and then the radius as a function of x, and then that function squared. I'm kind of cheating a little bit by writing the squared up top, but just know it's whatever the function is for the radius, all squared. We did a couple of examples in the last video. We're going to do a little bit more today. So I'm just going to go over to the book here, and we'll read through the question, and then we'll solve it. So we're looking at this example 6 here. Find the volume of the solid generated by revolving the region bounded by y equals square root x and the lines y equals 1, x equals 4 about the line y equals 1. So this one's going to be a little bit different because we're not revolving around the x-axis or the y-axis, we're revolving around a separate axis of rotation. So let's try to get our picture going here. So just to I'm going to have to get off the screen here, but just remember it's y equals square root x, y equals 1, x equals 4 is going to be the bounds for our region. So let's graph that out. So y equals square root x is, it's just this kind of graph here, and this goes on forever. Y equals 1 is going to be the horizontal line at 1 on the y-axis, and then x equals 4 is the vertical line here at 4 on the x-axis. So we're looking at this region. And we're going to take this region, and we are not revolving it around the x-axis. We're actually going to be revolving it around this line here, the y equals 1 line. So it's very similar to the question that we did a little bit ago in the first video, but now we're just changing the axis of rotation a little bit. Okay, so what we need to do is we need to come up with the formula for the radius as a function of x. Our radius is going to exist between this value here, which we need to figure out what that point is. It's pretty easy to see that that's going to be the value 1. Right, if I plug 1 into the square root of 1 is 1, and that gives me this 1 y value up here. So we're existing between 1 and 4, but my radius is not just going to be the square root x. We have to be a little bit more careful, because the square root x, if I'm here at location x, square root x is going to give me the entire y value all the way from the x-axis up to the top of the line. We only want from the top of the line down to this value of y equals 1. So I hope it's kind of obvious to see that actually the radius is going to be the square root x minus that distance of 1. So it's the total y value minus that 1 y value that we don't really care about. So this is going to be what we plug into this. I'm playing around with my pen here. Is going to be what we plug into the radius function. So just to do it real quick, the total volume is going to be the integral. We are going from 1 to 4, since that's where my region exists on the x-axis, of pi, and then my radius function, square root x minus 1, quantity squared, dx. Just to do this real quick, squaring that off and taking the pi out. So we pulled the pi out. We still have the integral from 1 to 4. We're going to have to FOIL this all out. So square root x times square root x is just x. Root x minus times negative 1, and there's going to be 2 of those, so negative 2 root x. And then negative 1 times negative 1 is positive 1. Just to do the antiderivatives of each of these, so we still have the pi like way out in front. X is going to go to 1/2 x squared. You want to think of this as being x to the 1/2. We're going to raise that up to 3/2 and then divide by 3/2, which is multiplying by 2/3. 2/3 times negative 2 is negative 4/3. and that's going to be x to the 3 halves. And then my 1 over here is just going to go to x, and then we're evaluating this between 1 and 4. If we were in class at this point, I would just put ... up on the board and then write out the final answer, but I guess just to be really clear about it so you can follow through, let's actually plug 4 into all of this minus plugging 1 into all of this. So we still have the pi out in front, and if I plug 4 into everything, and we're going to need some calculator stuff here, or at least I would, 4 squared is 16, 16 divided by 2 is 8, minus plugging 4 into here, 4 to the 3, 4 to the 3 halves is a number, it's 8. 8 times 4 thirds is 32 thirds. Plus 4 into x is just 4. That's going to be minus plugging 1 into all of this stuff. Plugging 1 into this first one is just going to give us 1/2. Minus into the second one, the 4 thirds. Plus the 1 into the x there is just 1. Combining all the like terms together, everything has a pi in it, so really we're just adding up all of these numbers. I'm going to cheat and look at what the book's answer is, because I do not feel like typing all that into the calculator. Here, 7 pi over 6 is the final answer that we get here. So if you plug all this into the calculator, I promise you it comes out to be 7 pi over 6. So that would then be the volume of this region revolved around the line y equals 1. It's that kind of funnel looking shape, like an ice cream cone kind of shape laying on its side. Okay, cool. I got one more example that I want to do here. And again, it's the one from the book. I'm not going to do the next example in the book. You guys can try this one on your own if you really want to. Example 7. I'm going to jump to example 8. Just because it's a little bit more difficult, and I think it'd be better to do the more difficult ones here together. Okay, so here we go. Example 8. Find the volume of the solid generated by revolving the region between the parabola x equals y squared plus 1 and the line x equals 3 about the line x equals 3. So first things first, let's talk about graphing stuff like this, because you're going to have to do that a lot in this class. It is difficult to graph this because your calculator can't really graph things unless you have it solved for y. You have a couple of different options here. The first option is to try to solve it for y, but when you do the square root, you have the plus and the minus. You would plug the positive version into the y1 of the calculator, the negative version into the y2 of the calculator, and just graph both of the lines separately. Another option for you is that you could use Desmos, of course. Just type this equation just like it is into Desmos to see what it looks like. And kind of your last result would be to switch the x and the y, graph it that way, which is really graphing its inverse, and then reflect that over the diagonal line. Do whatever you need to do to get the graph of this equation. Okay, so I think just the best thing for me to do here would be to graph it in Desmos. So let me do that real quick. Oh, all right, I'll pause it and pull it up. Okay, I see some troubles already with using this tablet thing, is that it's kind of hard to write stuff out because my keyboard's kind of under, it doesn't matter. Here we go, I got it. So here's Desmos, here's the graph. X equals y squared plus 1 is going to be the parabola here on the side that has the vertex here on the x-axis at positive 1. So I'm just going to go over to my notes here and let's try to sketch that out. So here's our xy plane. And then the parabola is going to be opening up to the right here where it intersects here at the value 1. All right, going back to the question in the book, the other part, right, so there's our parabola and the line x equals 3. The line x equals 3 is going to be a vertical line here at 3. So this region is the region that I have. All right, now we want to take that region and we want to revolve that around the line x equals 3. So we're going to be taking this shape and revolving it this way. All right, so it's going to make kind of like a ball-looking shape, like a squished ball, whatever you want to think of it. That's the shape we're going to be making here. Okay, so we're still using the disk method here. We're using the disk method because our region is... oops, I erased half of it. Because our region is still bounded against my axis of rotation. There is another method which we're going to talk about in the next video where your region is not against your axis of rotation. So we'll see that when we see that. The other problem with this question compared to the other questions is that we're revolving this around a vertical line, which means that my disks are not going to go along the horizontal axis. My disks are going to go along the vertical axis. So I just need to change up the formula for the disk method a little bit. It's still the integral. It still has the pi. But now your radius is not a function of x. Your radius is going to be a function of y, quantity squared dy. Oh, sorry about that. dy. So we are allowed to do the disk method along the y-axis instead, and we're going to have to do it whenever your axis of rotation is vertical. Okay, we need to come up with the radius now as a function of y. So let's just say that maybe we're here on the y-axis. My radiuses are going to exist from this intersection up to this intersection. You'd have to plug it in a couple of things to see exactly where that's going to be. I'm almost certain that this is going to be at, all right, so let's see. So this is at the value x equals 3, and if I plug 3 back into the equation, remember our parabola is from the equation x equals y squared plus 1. So if I substitute in a 3 there for this x, subtract the 1 over, I get 2 is equal to y squared, which means that this has to be at the y value positive square root 2. This one down here is going to be at the y value negative square root 2. So that's going to be the limits of my integral when I get there. Okay, so going back to the radius, let's say we're here at y. What we need is we need this distance, the distance from the graph itself all the way to the axis of rotation. I'm going to have to figure out how to get different colors here. But there we go. So that distance from the function to the axis of rotation is going to be the radius of the disk that we end up creating. Just to kind of re-sketch it over here so there's less stuff going on, let's say this would be the disk that I would end up with at the value y. So we need the radius of that disk, and here's where we have to be careful, because we just want this distance from the into the function to the axis of rotation. Okay, if I am at y and I plug y into my equation, it's going to give me the x value of that point right there. But that is going to be this distance from the point to the y-axis, and I don't care about that distance. So what I'm going to do is I'm going to take the total value 3, that's the horizontal distance to the axis of rotation, and subtract that x value right there, where that x value is the y squared plus 1. All right, so again, just to talk through it, it's the total horizontal distance of 3 to the axis of rotation, but we are subtracting this part here, because we don't care about that part. That's going to leave us with the only part that we do care about, this part here. Okay, now, just to simplify it, we do have to distribute that negative sign into the parentheses here. So 3 minus y squared minus 1. The 3 minus 1 is 2, and then we have the negative y squared. Then we plug that into our volume formula. So the volume is going to be the integral. We do have to be careful about the limits. Remember, it's that negative square root 2 to the positive square root 2 of pi, my radius function, which is 2 minus y squared, quantity squared, dy. All right, just to do this real quick, we're going to pull the pi out. We'll go ahead and FOIL out this parentheses here. So 2 squared is 4, or then we're going to have a negative 4y squared, and then plus a y to the 4th. So again, that was just foiling out the parentheses and pulling the pi out. Now we can do the antiderivative here. 4 is going to go to 4y. Negative 4y squared is negative 4/3 y cubed. And then the plus y to the 4th is going to go to 1/5 y to the 5th. And then we're plugging in negative root 2 to positive root 2. All right, I definitely don't feel like typing all this into my calculator and fiddling with it. I hope everybody is okay with that. Now that you're in Calc 2, you can plug numbers into all of this stuff and simplify it all down. So just to kind of get the final answer from the book here, it is this awful looking thing, 64 pi root 2 over 15. Okay. Great. So If you need to, go back and look at a couple of the exponent rules, because you're going to have these root 2 cubes and then the root 2 to the 5th. So just to kind of show you what that would be, if you have square root of 2 cubed, remember that's just going to change to 2 to the 3 halves. This one here, the root 2 to the 5th, would change to 2 to the 5 halves. And then you can play around with this to simplify it back down over here. If anybody needs help, like simplifying it down, I don't mind making like a separate video of plugging this stuff in and simplifying it, but it would take me another 5 minutes to do all that. And I hope everybody's okay with getting this answer. Okay, cool. So again, so far we've only been doing the disk method where your region is up against the axis of rotation, and that's not always going to be the case, like you'll see in the next video.